Hi students, we're going to talk about the idea of a limit now. A lot of students have trouble with this concept, but don't let it fool you. It's not really that difficult if we think about the intuitive meaning behind it. It's giving us a way to determine if we have a value of x here, and we'll call it c, that as we're getting closer and closer to c, from both sides, maybe x is bigger than c, so I'm coming from this direction. If I follow my graph here, I'm coming down here, down the graph. Or if the value of x is smaller than c, I'm coming up the graph. So what's happening is that as I approach, as x gets closer and closer to c, the limit as x approaches c of the function f of x, well, what height is it approaching? The height which we'll call L for limit. It's a way for us to understand better the idea of approaches, so as approaching a value of x. Limits can be numbers. Often they are numbers. Limits can be 0. Sometimes limits don't exist. And sometimes we have limits that are only from one side, which we call the left side if I'm coming towards c from values of x smaller than c. Or we have limits from the right if we're coming from values of x larger than c. So we have a lot of different types of limits. We have a lot of different approaches to take while we evaluate these limits. So let's start with a few examples. So if we wanted to just evaluate the limit as x approaches 4 of f of x, and if f of x is equal to, I'll write it over here, x squared plus 4, we would put in x squared plus 4 into that limit statement. So what would we do here? The first thing we always want to try is just replace the value of x into your function. So since x is approaching 4, I would replace x in my function with 4, and I'll need to square it and then add 4 because that's what my function is, x squared plus 4. So when I compute 4 squared, I get 16, and then plus 4, that means this limit is 20. So that idea of L here, the limit is equal to 20. Let's try another problem. The limit as x approaches 2 of x squared minus 4 divided by x minus 2. So what happens now if we just replace x in our function? So our function now, I could call it f of x, g of x, h of x, doesn't matter. I'll just use f of x again, is equal to x squared minus 4 divided by x minus 2. And my function then goes right in there next to my limit notation. Now, if I just replaced x with 2, I would get 2 squared minus 4 divided by 2 minus 2, which would be 4 minus 4, which is equal to 0, divided by 0. So I'd have 0 divided by 0. When you see that 0 divided by 0, that's called an indeterminate form. Now the problem with this is that you can't just stop here. You can't just say, okay, I'm done, it's indeterminate. Because sometimes we might be able to manipulate this function a little bit and have it actually turn out to be a limit that's a number. So when we see this indeterminate form, 0 divided by 0, we want to think about something else. I'm going to erase this part right here. And I want you to think about, can I do something else with this function? Can I manipulate it in some way so that way I can actually compute the limit? Well, let's think about it. Does x squared minus 4 sound familiar to you? What could you think about doing with that? If I do this, what am I talking about? I'm talking about factoring it. So it's a difference of squares. So we know that it's going to be x minus 2 times x plus 2 is going to give me, when I multiply those back through and FOIL them, it's going to give me x squared minus 4. So just by factoring one or both of the values in the expressions in the numerator or the denominator, x minus 2 can't be simplified any further, so I only had to factor the numerator. You can see that we have the same term above and below the division sign. So we can remove those. Well, now this becomes an equivalent form of the limit as x approaches 2 of x plus 2. Now that I've simplified this, I can just replace x with 2, and I have 2 plus 2 is equal to 4. My limit of this function, number 2 here, is actually equal to 4. So the point is, don't stop when you see that it's 0 divided by 0. And by the way, 0 divided by 0 is not 0. It's undefined division because we cannot divide by 0. And that's why we give it a special name of this indeterminate form. Students, let's try another problem. Let's take the limit as x approaches 1 of x minus 1 divided by x squared plus 1. Now if you replace x with 1, you'll have 1 minus 1, which is 0, divided by 1 squared plus 1, which is 1 plus 1, which is 2. Please note that this is not possible to, it's not possible to factor x squared plus 1. There's no way to get two binomials that when you multiply them together, that middle term is gone and you get a positive 1 here. It doesn't work. So that's why this is our only possibility, just replacing our x value with the number that x is approaching. 0 divided by 2. 0 divided by 2. Well, what number do I multiply 2 by to get 0? It's 0. So bottom line, what this means is 0 divided by 2 is equal to 0. And that's fine. It's fine for a limit to be equal to 0. It's not bad. It's not a bad thing. It's possible. I have another problem for you. The limit as x approaches 1 of x minus 1 divided by x squared minus 1. Now, if we replace x with 1 here, we're going to have a problem here because we're going to have 1 minus 1, which is 0, divided by 1 squared, which is 1, minus 1, which is 0. We're going to have one of those indeterminate forms. So let's think again, what could we do to this function to write it in a different way and simplify it? X minus 1 can't be simplified, but x squared minus 1, that's a difference of squares. So that can be written as x minus 1 times x plus 1. The x minus 1 is gone from the numerator and the denominator, but keep in mind something, that it does leave a 1. What you're doing here in shortcut is you're factoring out a factor of x minus 1 from the numerator and from the denominator. And it's leaving you with a 1 divided by x plus 1. Watch out for that because that can be it can be tempting to think that the answer here is x plus 1, but it's not. It's 1 over x plus 1. So now if we compute the limit of this new function that we've just simplified from the original function and replace x with 1, we will get 1 over 1 plus 1, or 1 over 2 as our limit. Bye. So welcome back. We're going to do a few more problems with limits, evaluating our limits for a value of x. So here we're saying this is the limit as x approaches 8 of this function, which is a rational function, x squared minus 4x minus 32 divided by x minus 8. So without even looking at the numerator, the denominator is already going to give me problems because I can see here that I'm going to have something divided by 0. Division by 0 is not allowed. Division by 0 is undefined. So we can't entertain that. We can't even try to do anything with that. Which this is telling me that I need to do something else because that's not going to work, just plugging in the value that the limit of the x is approaching. So because I see a rational function, immediately I think again, how about factoring? So let's try to factor that numerator. So if I have x squared minus 4x minus 32, I use the little x method here, that I want a product, meaning two numbers that multiply together to get negative 32, and I will want a sum of my middle term coefficient, which is negative 4. So if I think about factoring 32, I could think of it as 1 times 32, 2 times 16. 3 doesn't go into 32. How do I know that? Because 3 plus 2 is 5. You add up the digits of a number, and if it's divisible by 3, it will be a multiple of 3, that sum. So because it's 5, I know 3 will not go into 32. Well, I know that 4 times 8 is 32, and that's an interesting one there because I can see that I could take combinations of 4 and 8. One of them is going to have to be negative for me to get a multiplication or a product that's negative 32. And if I need a negative sum, then it means that the larger value, the 8 is going to be the negative number. So negative 8 times positive 4, that's going to give me my negative 32. Negative 8 plus 4 is going to give me my negative 4. So what do I do here? This will help me form my two binomials to factor x squared minus 4x minus 32. I will want x minus 8 in the first binomial, and then x plus 4. Keep in mind you could reverse it in the sense that this first binomial could be x plus 4, the second one could be x minus 8. Order doesn't matter when we multiply, but the order of the minus and the plus most definitely do matter, because the only way to get that middle term of negative 4 would it be to have this negative 8x plus a positive 4x if I were to FOIL this out. That would give me my correct binomial terms here. And that works out really well here because of the x minus 8. If I factor out an x minus 8 from both numerator and denominator, that's going to leave me with x plus 4 in the numerator and then 1 in the denominator, because I will have factored out x minus 8. X minus 8 divided by x minus 8, that's equal to 1. And that's why this leaves me with x plus 4. So now we're looking for the limit as x approaches 8 of x plus 4, an equivalent expression to our original one that we could not find the limit for. Now replacing x with 8, I will have 8 plus 4, and my limit is equal to 12. Remember, the limit is the height of the function at that value of x. In this case, it was 8. So if x is 8, the height is approaching a y value or f of x value of 12. Bye. Before we get started on limit problem number 6, I want to tell you about a very nice program online that you can find called Wolfram Alpha. I think Wolfram's somebody's name. And it's very easy to use. You can just put in any function you have, including limits, and it will give you the answer. It will also show you how it's found. But more importantly to me is that it'll graph it for you, and it'll help you see if your answer that you found through algebraic manipulative measures like we've done is correct, and you'll see the graph of the function, so you can kind of put them together, put the visual along with the computational together to make sure that you are understanding why the limit is what you are getting. Let's try another problem. Let's take the limit as z approaches 1. So we can have any variable here. It doesn't have to be x. We'll use z this time. Of 7z cubed minus 6z. Okay. So when I look at this function, it's a polynomial. Polynomials have limits. All I have to do is replace z with the value that it's approaching, which is 1. So we'll have 7 times 1 cubed minus 6 times 1. 7 times 1 cubed is just 7 times 1, which is 7. And 6 times 1 is 6. So we have 7 minus 6, which is equal to 1. Our limit as z approaches 1 of this function is equal to 1. The height of the function, the y value, or the f of z, is equal to 1. Welcome back. We're going to talk about now limits at infinity or negative infinity. So if we have this problem, for example, the limit as x approaches infinity of this function, this cubic function, 2x cubed minus x squared plus 6x minus 4. So keep in mind, if x is approaching infinity, it means x is getting bigger and bigger and bigger. What's the behavior of this function? What height or what value of f of x is this function approaching? We have to talk about this theorem. We have a theorem for limits of power functions at infinity. And if we have for real numbers k and p, we have the following theorems. The limit as x goes to negative infinity, if we have a function that's k divided by x to the p, you can think of this as 1 over x and then to a power multiplied by a constant k. K could be 1 or k could be any real number. The limit of that function is going to be equal to 0 because what's happening as x is getting smaller and smaller and smaller, negative numbers, like 1 over negative 5, negative 1/5. 1 over negative 10 is negative 1/10. You're getting closer and closer and closer to 0. And that's why that function's limit is equal to 0. The same goes for whether you're talking about a limit as x is approaching negative infinity or x is approaching positive infinity. You'll still have 0 because as x is getting bigger and bigger, I'll just use this as an example. 1 over x squared is going to be 1 over 4, 1/4. 1 over x to the 10th, 1 or 1/10, 1/20, 1/30. The larger this denominator gets, the smaller our fraction is getting. And then what's happening is that it's getting closer and closer to 0. When we have limits of a function that's just a power function, x raised to a power, but it's multiplied by a number like k, and k could be 1 or k could be anything, then what's happening is as x is approaching negative infinity, that value of x is getting smaller and smaller and smaller. So it's not going to ever reach a limit. It's just going to continue on to negative infinity. It could be also positive infinity depending on the value of k. If k is a negative number, then we would have a limit of a positive infinity because we would have a multiplying a negative number times a negative k. Here, if k was positive and x was approaching a positive infinity, x is getting bigger and bigger and bigger, we have x raised to some power is going to it's just growing without bound, without limit. And multiplying it by k, if k is positive, then we would eventually reach no limit, which we imply would be a positive infinity as our limit. That would be our height. It's just never going to reach a limit, really. Or it would reach negative infinity if k was negative. So here's how we approach these problems where we have a limit as x goes to either negative infinity or positive infinity. We want to try to think about factoring or doing something so that we see something that resembles this, 1 over x to some power. I'm going to factor out here x cubed from each term. That's going to leave me with a 2 here. And then if I take out x cubed, it's like I'm dividing each term by x cubed. So if you think about it, x squared divided by x cubed would be 1 over x, because it would, using the power rule for a quotient rule, I should say, I would subtract the exponents. 2 minus 3 would leave you x to the negative 1, which is 1 over x. So I would have 1 over x. And then in a similar way, I would have 6 over x squared, because it would be like I was taking 6x and dividing it by x cubed. I would have 6 over x squared, and then minus 4 over x cubed. So what's happening here, as x is going to infinity, what's happening to each of these terms that's a fraction? Well, x is getting bigger and bigger and bigger, so therefore 1 over x is getting tiny, tiny, tiny. Think of it as x is starting at 10, or 1 to 10 to 100 to 1,000, a million. 1 over a million is very, very tiny. Our limit for this term is that it's approaching 0 using our power or theorem right here. Same goes for this one, and same goes for this one. They're all approaching 0 due to our power function limit at infinity. So we're left with then the limit as x goes to infinity of x cubed times 2, so this would be 2x cubed. Well, what's happening as x is getting bigger and bigger and bigger, you can think of this 2 as our k down here. X cubed is growing huge, growing without bound. We will have this limit will be infinity, which really means it does not exist. There is no bound. There is no limit. That's numeric. I encourage you to do several problems with these limits at infinity. They can be a little tricky, but working a few of them, 2 or 3 of them, will start to give you the idea and start to help you remember to use these theorems here, because they're really the key to solving these problems. Bye, students.